Today I'm going to be completing part A of homework 2 for process dynamics and controls. And what we're going to be doing today is splitting up a PFR into a bunch of different CSTRs to simulate the backmixing that happens when you've got a pulse of concentration coming into your PFR. So to draw this out a little bit, say we were looking at a PFR, something like this. You got your flow coming in, your flow going out. Let's say you can model your concentration, and all of a sudden you've got a spike in one of your components coming in. Now, in a plug flow reactor, what that's going to look like is a plug. It doesn't really get that fully developed flow that you'd expect. It comes in as a flow with no backmixing. That's not how these things look in reality. So to simulate this, we're going to split up our PFR into a set number of CSTRs. And we're going to say that each of these sections is a CSTR. So if you're looking at your first section, we can simulate that as our first CSTR, and any of the back mixing occurring is going to be simulated by the mixing that happens in this CSTR. And we can go ahead and break this PFR into a very large number of CSTR to get to where we're almost seeing tubular plug flow. And in this case, we're going to simulate a PFR with a total volume of 100 liters. And we're going to simulate this PFR as 100 CSTRs, which is going to be our N we showed here. And to get the volume of each of our CSTRs, we're going to take our total volume divided by our N. Now that we got this problem set up, we know the idea of what we're trying to do here, we can go ahead and move into Python and try to get a graph of what this plug is going to look like. Because as I said, when you have your first pulse of concentration there, over time, you're going to see band broadening as it gets mixed in each of these different CSTRs. So by changing our amount of N, we'll be able to see how that affects the band broadening. Like in this case, you've got your first plug. But once it comes out of here with all the mixing that occurs in each of these stages, this plug might look something more like this versus a rigid plug that came in. So let's go ahead and move into Colab and see how this is going to look simulated using Python.
All right, so moving into Python, I'm going to go ahead and copy and paste our initial values. And like I set up on the board there before, our n equals 100 is going to be our amount of CSTRs that we're going to use to simulate our PFR. Our total volume, as I said before, is going to be our 100 liters. Our V is going to be the volume of each of our CSTRs. So we're going to take our total volume divided by our n, the amount of CSTRs we have. Our starting inlet flow rate is going to be 100 liters per minute. Our initial concentration across the entire PFR is just going to be 1 mole per liter. And we're going to put that into an array so that we can define that concentration for each of the CSTRs that we're using to simulate our PFR. And then later on, once we go ahead and define some functions, we're going to check the concentration at 10 different times throughout our PFR so that we can graph it a little bit later. So we're going to go ahead and move on and start defining some functions. Our first function we're going to put in here is we're going to define our sigmoid. as a function of x naught, which we're just going to have equal 0 for now, and our width, which for now we're just going to set equal to 1. And what this is going to do is, as we were talking about up on the board, the bands can have really sharp, blocky shape as it's coming in, or more realistically, you're going to need a curve to come up. Regardless of how steep the curve is, it can't just be like a right angle jump. It has to be like curved into it. And to do that, we're going to utilize a logistic function. So the graph is going to take more of a log type shape. And as we adjust that width, we can make it look more like our blocky shape, or we can widen it out by increasing that width later on. But for now, we're just going to define this function so that we can get that shape into Python, and we can later apply it to our PFR and get our graph that we're going to need. So moving on from this, we need to actually put in the function that calculates the sigmoid, the logistic function, which is going to be a scipy function, and return sp.special, I believe, .xpit. And we're going to do x equals do x minus x naught divided by our width and that should give us, like I said, that shape that we're looking at for our logarithm, so that we can kind of plug that into our actual equation and get a shape that makes sense, that looks like a pulse once we go on to plotting. So now that we've got our sigmoid function, we're going to need to bridge the gap from this kind of vague, like, logarithmic shape that we were talking about, getting the shape, to our actual concentration, so the actual problem. So we're going to define our pulse, that is the pulsing concentration, as a function of x, x1, x2, c1, and c2, because the C1 and C2 is going to be the concentration before the pulse, or like right as the pulse is starting, and the concentration at like the end of that pulse. And then an X1 and X2 is just going to be the length of the pulse, I should say. And then we're going to have our width again equal to 1, just in case we don't put a value in there. Moving on from there, we can go ahead and return this behemoth of a function. We're going to have our C1 plus our C2 minus C1 times our sigmoid with x naught is going to equal x1 for this first part, and our width is going to equal our width defined earlier, and then no comma there, minus our C2 minus C1 times our sigmoid x equals to x2 this time, and our width x naught equals to x2. And our width is again going to equal previously defined width. I believe that looks all good. Shift enter. All right, worked out. So to check and make sure that we're kind of making these pulses right before we move into the actual problem of simulating a pulse height with an additional 3 moles per liter, we're just going to kind of plug this into a plot. So I'm going to say fig equals make subplots. I'm going to do x equals np.linspace, going from 0 to 10,000 values in between. And then I'm going to do figure.add scatter, have x equals x, y equals pulse of, I'm going to do x, I'm going to go from, have x1 be 1, x2 be 2. And then we know from the problem that we're going to be working with later that our initial concentration is going to be 1 mole per liter. So we're going to have C1 be 1. Then we're going to add our additional 3 mole per liter pulse, which is going to bring us up to 4. And then finally, we're going to have our width be 0.01 for now. But we'll move that around so we can kind of see what the implications of the width are, how they change, how broad the band is, the curve versus the really sharp edges. So let's go ahead and see if that worked. Figure object has, hold on, put an underscore there. Shift enter. Look at that. So this is going to be our pulse that we're trying to simulate. And all of this has pretty much just been to get that shape down so that we can later make our nice pretty plot. So moving on from here, we're going to go ahead and start digging away at this actual problem we've got up here. All right, now moving on to our actual function, we're going to go ahead and define our right-hand side as a function of time and our vector. And then we are going to go ahead and define our initial pulse coming in. So we're going to say our Cn, that initial concentration pulse, is going to equal our pulse function. Our x is equal to our time. So that's going to be our x-axis, the seconds as the pulse moves down. And then we're going to put in our initial time, which is 0, then 1, and then our initial concentration, which is 1 mole per liter, and our pulse that we're adding in, so we're adding another additional 3 moles per liter, so that's going to bring us up to 4. And then finally, we need our width, and we want this to be pretty boxy, so we're going to say it's 0.01. Moving on from there, we can go ahead and find our vector as RC, our concentration. And then moving on from here, we are going to need to find the change in concentration as we move down our CSTR. So initially, we're going to define DC, our change in concentration, as an array of zeros like n. So array of zeros the size of our amount of CSTRs so that we can go in and then update each of those values. We're going to say DC is going to equal to NP dot zeros n. Then we are going to say that our initial change in concentration, so DC at 0, is going to equal our Q times our C in minus our C at 0, our first CSTR, all divided by our volume. And then moving on from there, all the rest of our values are DC at 1 onwards is going to equal our Q times our C at our previous CSTR for each step. So it's going to be C at -1 minus our C at 1, all again divided by V. And then we can finally go ahead and return our DC, our change in C, so that we can later stick that into a solve IVP function. So let's move on and go ahead and do that. Right now that we have our right-hand side, we can go ahead and solve our right-hand side based on our times so that we can create our plot of our pulses as they move down the PFR that's simulated by these CSTRs. And to do that, we are going to start out by saying that n times is going to equal 10. That's going to be the amount of times we're going to look in and check on our concentration profile at each throughout the time interval. So set that's 10 for now. And then we're going to say that our t plot is going to equal np dot linspace going from 0 to our n time with n times intervals. So that's our t-plot. We're going to go ahead and solve our right-hand side that we were talking about up above. So we're going to say that our result is going to equal scipy.integrate solve IVP of our right-hand side going from 0 to t end, starting at initial concentration of our C naught array. We use the RADOW method, and we're going to set our dense output to be true. And then finally, we can go ahead and create our C profiles, our concentration profiles, by solving our IVP up here for our t-plots. Looks great. And then finally, we can go ahead and move on and plot this out. All right, so let's go ahead and create our plot. So to get started with that, we're going to say fig equals make subplots as usual. And then we're going to do a for loop so we can go through for each of those n times and create a different profile for our concentration as we go down our CSTR simulation of our PFR. So we're going to say, so for T index in range n times, you're going to do figure dot add scatter. We're going to have our x equals np dot a range n to kind of create those CSTR profiles of size n as our x. We're going to have y equals c profiles going from to our t index. And then that should just about do it. Put a little colon up there. Finally, we're going to go ahead and show our figure. Let's see how this looks. All right. So yeah, you can see here we are getting up to our concentration at that first trace initially. But I think we are having some round off errors at the end here. So I'm going to go ahead and try to increase our end times and see if we can get a plot that's a little bit easier to explain. So we do 50. All right, so that's making a little bit more sense. As you can see here at our so if we isolate our first one, you can see our pulse coming in. Hasn't quite made it down. And then it goes down a little bit farther into here. And you can see as it starts to decrease, as it's moving through all of our CSTRs, this makes perfect sense. Yeah, coming here at the end, you can see our pulse is leaving once we get to around trace 45. But as you can see, we've simulated this pulse as it moves down through the plot. And to make this a little bit more discrete, maybe we can try to go ahead and increase our width. Well, I wouldn't say that's much more helpful in demonstrating what I'm talking about, but in that initial example where we increased our end times, you can definitely see how the pulse is moving through our PFR demonstrated computationally. And I think that, go ahead, and it has wound up our homework 2 part A. So I will see you in the next video.